Welcome to Daily Papers, the podcast where we break down the latest and greatest research into bite-sized conversations.
So, I have a question for you. When you think of space exploration, what pops into your head? Is it astronauts planting a flag, or is it maybe one of those cool, lonely rovers trundling across the surface of Mars?
Definitely the rover, but the reality of those rovers is a little less sci-fi than you might think. We can't just tell the Mars rover, go check out that cool rock over there, and have it zip off. There's a huge time delay, up to 20 minutes each way for a signal to get to Mars and back.
20 minutes. So every single move has to be planned meticulously, hours or even days in advance, by a team of people back on Earth. It's incredibly slow. And that's for Mars. If we want to explore even more distant places, like the icy moons of Jupiter or Saturn, that delay becomes hours, or we might lose contact for weeks.
Exactly. We need robots that can think for themselves. And that's the central question of the paper we're looking at today. It's titled Risk-Guided Diffusion Toward Deploying Robot Foundation Models in Space, where failure is not an option.
I love that subtitle. It's very dramatic, but for a multi-billion-dollar space mission, it's absolutely true. So what's the big idea here? How do we build a robot we can trust to not drive off a cliff on another planet?
Well, the first thought is to use modern AI. We have these incredible new AI systems called foundation models. Think of the technology behind things like ChatGPT or AI art generators. These huge models are trained on vast amounts of internet data to understand language and images.
Right. So the idea is to build one for robots. You train it on millions of hours of driving data, show it a picture of its goal, and it should just know how to get there. It can understand abstract goals like navigate towards that geological feature that might contain water.
Precisely. And in many cases, this works brilliantly. But there's a massive catch. These models are only as good as the data they were trained on. If a robot encounters something completely new and unexpected, what the paper calls an out-of-distribution scenario, it can fail catastrophically.
So if the AI has only ever seen pictures of red, rocky deserts, and it suddenly comes across a patch of slippery blue ice, it might not even register it as a hazard. It might just try to drive right over it.
That's the exact problem. In the paper's own tests, the standard off-the-shelf AI model had a safety failure rate of 100%.
100%? It crashed every single time?
Every single time, because the test environments were designed to have hazards the AI hadn't seen before. So a super intelligent AI is great, but it's also brittle. It lacks common sense and a fundamental understanding of real-world physics when things get weird.
Okay, so the purely AI approach is too risky. What's the solution? Do we just go back to manually controlling it from Earth?
This is where the paper gets really clever. The authors took inspiration from human psychology, specifically from a famous concept called thinking fast and slow. The idea is that our own brains have two different modes of thinking.
Oh, I think I've heard of this. There's System 1, which is our fast, automatic, intuitive gut reaction, and System 2 is our slow, logical, effortful thinking.
You've got it. So the researchers decided to build a robot brain with both of those systems. Their System 1 is that fast, powerful AI foundation model. It's the creative, intuitive part that looks at the scene and says, let's go that way, the goal is over there.
It's the impulsive adventurer. So what's the robot's System 2, the slow, careful thinker?
System 2 is what they call a physics-based risk estimator. It's not a learning model. It's more like a cautious engineer. It uses the robot's actual sensors, like lasers and cameras, to build a detailed 3D map of its immediate surroundings. Then it uses the laws of physics to calculate the actual risk.
So it's the part that says, hold on a second. According to my calculations, that slope is 35 degrees and the ground is loose gravel. If we go there, there's a 95% chance we'll tip over.
Exactly. It's the voice of reason. It grounds the AI's ambitious plans in the cold, hard reality of physics. The true breakthrough of this paper is how they get these two systems to work together.
So how do they do it? Does the AI just propose a path and the physics checker gives it a thumbs up or a thumbs down?
It's actually much more collaborative than that. The AI they use is a specific type called a diffusion model. The simplest way to think about it is to imagine a sculptor. They start with a random block of marble, just noise, and slowly, step by step, they chip away until a clear shape emerges.
Okay, so the diffusion model starts with a random, nonsensical path and slowly refines it step by step into a coherent route from A to B.
Right, and this is where the risk-guided part of the title comes in. At every single one of those tiny refining steps, the physics-based system 2 is looking over the AI's shoulder. It's constantly providing feedback.
So it's not waiting until the end to say that's a bad path, it's steering the process from the very beginning. As the AI is forming the path, the physics model is saying, ooh, careful, that bit looks a little risky, let's nudge the path a little to the left here. Okay, that looks safer, now keep going.
That is a perfect analogy. It guides the creation of the path to be safe from the ground up. This means the robot can intelligently navigate around a hazard rather than just planning a route that crashes and then having a simple filter stop it at the last second.
That makes so much sense. So the big question, did it work in the real world?
It did. They tested it at a facility at NASA's Jet Propulsion Lab called the Mars Yard. It's basically a big, realistic Mars sandbox for robots, filled with tricky rocks, slopes, and other hazards.
And what happened? We know the pure AI failed 100% of the time. How did the fast and slow thinking robot do?
It was a huge improvement. Their method reduced the safety failure rate by up to 4 times compared to other approaches, while still being just as successful at actually reaching its goal. It found a beautiful balance between getting the job done and, most importantly, staying safe.
That's incredible. It's like they gave the brilliant but reckless AI a wise, experienced co-pilot to keep it out of trouble.
That's exactly it. This hybrid approach makes these powerful new AI models robust enough to be trusted on missions where, as the title says, failure is not an option. It's a major step towards having truly autonomous explorers on distant worlds.
It's not just about making the AI smarter, but making it wiser. Combining the creative power of machine learning with the grounding force of physics. What a fascinating concept.
A perfect partnership for the final frontier. And that's all the time we have for today's Daily Papers.